There's this invisible force all around us. I mean, it literally powers our entire world. It holds the very atoms of our bodies together. And, well, sometimes it gives us a little shock. So today, let's pull back the curtain on one of the most fundamental ideas in the entire universe, electric charge. You know exactly what I'm talking about, right? That sharp zap you get from a doorknob in the winter? Or when you pull off a sweater in the dark and hear it crackle? Turns out, those aren't just random annoyances. Nope, they're actually clues. Clues pointing to one of the most powerful forces there is. And today, we're going to follow those clues and crack this mystery wide open.
All right, so to really get our heads around this, we need to take a trip back in time. Way back. Back to the very first moment someone looked at something and thought, that's strange.
So, our story kicks off around 600 BC with an ancient Greek philosopher, a guy named Thales of Miletus. And what he noticed was that when he rubbed a piece of amber, it suddenly got this weird power. It could attract light stuff, like little bits of feathers. Now here's the cool part. The Greek word for amber is electron. Sound familiar? Yep, that's literally where we get our modern word electricity. Pretty neat, huh? Okay, so people knew about this weird attraction thing for centuries. But the next big question, the real leap forward, was figuring out the rules of the game. How does this invisible force actually work? So scientists started running these super simple but honestly brilliant experiments. They take a glass rod, rub it with silk, and then bring it near another glass rod they'd rubbed with silk. And what happened? They pushed each other away. They repelled. Then they tried it with a plastic rod and some cat's fur. Same thing. 2 of those charged plastic rods, they also repelled. But, and this is the absolute key, when they brought the charged glass rod near the charged plastic rod, they pulled towards each other. They attracted. This all led to a huge realization, and the person who really nailed it down was Benjamin Franklin. He figured, hey, there aren't tons of different kinds of this stuff. There are only 2. And he's the one who gave them the names we still use today, positive and negative. Just by convention, he called the charge on that glass rod positive and the one on the plastic rod negative. And right there, that simple experiment gives us the fundamental rule that governs, well, everything in electrostatics. It's so simple, but it's incredibly powerful. Like charges repel, opposite charges attract. That's the whole game. But wait a second. This brings up a pretty big question, right? If everything around us is made of these charges, why isn't my desk constantly flying away from my chair? Why isn't everything always zapping and attracting everything else? And when you rub 2 things together, what is actually moving from one to the other?
Well, the answer comes down to one tiny fundamental particle, the electron. It turns out, when we're talking about static electricity in solid objects, the only thing that's actually doing the moving, the only thing hopping from one object to another, is the negatively charged electron.
So here's the breakdown. Most stuff just sitting around is electrically neutral. That means it has a perfect balance of positive and negative charges. Now, when you rub 2 things together, you're not creating any new charge out of thin air. All you're doing is shuffling those electrons around. You're giving some of them just enough of a kick to jump ship from one object to the other. So the object that loses electrons ends up with more positives, making it positively charged. And the object that gains those extra electrons, well, it becomes negatively charged. It's just a transfer, that's all. This explains why you can charge up a plastic comb by running it through your hair, but you can't really do the same thing with a metal spoon, right? It all comes down to one key difference. Some materials are conductors. Think metals, our bodies, the earth. In these, electrons can zip around freely. So if you put extra electrons on a metal spoon you're holding, they just flow right through you and into the ground. Poof, gone. But other materials are insulators, like plastic, glass, or wood. In these, the electrons are held on tight. They can't move around easily. So when you put a charge on an insulator, it just stays there. It's stuck. Okay, so we know what charge is, and we know it's the electrons that are doing the moving. Now, let's get into the really cool part. The 3 unbreakable laws that charge always follows. Rule number 1, it's called additivity. And honestly, it's as simple as it sounds. It's just basic math. If you've got a bunch of different charges in a system, the total charge is just what you get when you add them all up. You just have to remember the signs. So a +5 charge and a -2 charge together, that gives you a total of +3. Easy. Rule number 2, conservation. Now this one is a really big deal in physics. It means you can't create or destroy electric charge. It's like money, you can't just print it out of nowhere. Think back to that glass rod and the silk cloth. Every single electron the rod lost, the silk cloth gained. The total amount of charge in that little system, the rod plus the cloth, stayed exactly the same before and after. It was just moved around. And rule number 3, this one to me is the most mind-bending of all. It's called quantization. What this means is that charge isn't some smooth, continuous liquid. Nope, it comes in tiny individual packets. It's like Lego bricks. You can have 1 brick, or 2 bricks, or 5 million bricks, but you can never have 1.5 bricks. The smallest possible chunk of charge is called the elementary charge, and we just call it E. So just how small is one of these packets? I mean, it is unbelievably tiny. We're talking about 1.6 times 10 to the negative 19 coulombs. That's a decimal point followed by 18 zeros and then a 1/6. It's so small that in our everyday lives, charge seems totally smooth and continuous. For the same reason, a high-res photo looks like a smooth picture instead of a bunch of tiny dots. All right, so we've got the rules. We know what charge is, we know it's electrons moving around, and we know it comes in these tiny little packets. So what's the last piece of the puzzle? Figuring out how to actually measure the force that all this charge creates. And for that, we have this guy to thank, Charles Augustin de Coulomb. Back in 1785, he built this incredibly delicate device called a torsion balance. It was so sensitive it can measure the unbelievably tiny pushes and pulls between little charged spheres. And from those painstaking experiments, he gave us the mathematical law that describes this invisible force perfectly. And what he found, now known as Coulomb's law, is just beautifully simple. It basically says 2 things. 1, the more charge you have, the stronger the force. Makes sense. And 2, the force gets weaker the farther apart the charges are, but it gets weaker fast. It drops off with the square of the distance. So if you double the distance, the force is only 1/4 as strong. Now get ready for this, because this leads to a truly staggering fact. We tend to think of gravity as this super powerful force, right? It holds us on the planet. Well, on the atomic scale, gravity is an absolute lightweight. The electrical force between a single proton and a single electron is, wait for it, about 10 to the power of 39 times stronger than the gravitational force between them. That's a 1 with 39 zeros after it. That number is so huge, it's basically impossible to even imagine. That's how much more powerful the electric force is. And here's the real takeaway. This mind-bogglingly powerful force, it isn't just some weird thing that happens in a lab. It's everything. It is the literal glue that holds atoms together, which holds molecules together, which holds you together. The only reason you're not falling through your chair right now is because the electrons in your body are electrically repelling the electrons in the chair. It's the force of chemistry. It's the force of biology. It's the force of life itself. Which brings us to one last big question to leave you with. If the electric force is so enormously, ridiculously powerful, trillions and trillions of times stronger than gravity, then why is gravity the force we notice? Why is it gravity that holds us to the Earth and keeps the planet spinning around the sun? Think about it. The answer takes you right back to the very beginning of our story today.